welcome to this manufacturing process technology part 1 module 42. We will be today discussing mostly about the temperature rise in the cutting zone because of the various portions of the power consumed in the primary, secondary and the tertiary zone of the cut. So let us actually understand the problem a little clear as to what these different zones are in metal cutting. So when a material is deformed elastically, some energy is spent to increase its strain energy, which is returned during the unloading, right. So some energy is spent to increase its strain energy, and obviously because it is in the elastic range the material will return back. So this is returned during the unloading process, which is returned during the unloading process. However, if it is a plastic case or it is basically plastic deformation, most of the energy is spent in converting or getting converted into heat and temperature rise of the material, right. So just write it down here that but in plastic deformation, and by the by most of the metal machining processes are based on plastic deformation, and so therefore 99% of the energy in that case is converted into heat energy. So in the plastic deformation, most energy is spent for conversion into heat, in case of machining, because most of it is based on plastic deformation, almost 99% of the energy is converted into heat. So obviously it brings a very strange situation that because of this heat flow into the three components which are actually connected to each other in machining, one is the workpiece, one is the tool and one is the chip, obviously the heat is going to get there would be a heat flow from the cutting zone into all the three components, that is the chip, the workpiece and the tool, and obviously there would be a temperature rise because of that. So if we are using a condition where because of the continuous power consumption of cutting there is an increase in the heat, it may lead to the deformability of the tool or change in the properties of the tool, and it may also simultaneously result in change in the material properties of the workpiece material, because things like let us say shear, yield stress etc. vary a lot based on what is going to be the temperature of the cutting zone. So in any event there is going to be an overall change because of this rise in the energy level and retained energy level in terms of temperature state, which comes on to the chip as well, this workpiece as well as the tool, and it creates a situation where we need to estimate now what is going to be the temperature rise because of all this energy flow or all this power which is consumed in doing the machining operation. So especially for ferrous metals, and maybe some other high strength materials like ferrous metals, with machining the temperature rises with speed of machining, and the tool strength also decreases. So obviously it would create more tool wear, and sometimes even tool failure, okay, if the temperature is abnormally high. So, this definitely should put a limit then to the cutting speed. So, limit the cutting speed, and that is why an analysis is needed, that how much would be the kind of optimum speed which would be needed for all these different failure aspects to not creep in and have the machining operation carried out at a certain optimum speed. So, if you look at how the chip formulation process again takes place, I am going to just draw the work zone in case of a chip formulation process. So, this right here is, let us say, the chip which has been created, and this right here is again the tool which on which, or on the surface of which, the chip rests. And let me just show these two boundaries of the tool face with these shaded regions. This is the tool, this is the workpiece, this is the chip. So, obviously, the major plastic deformation, if we look at, because of the temperature rise and the heat flow is a function of where this deformation is most. So, the major plastic deformation occurs in the shear zone. So, when this chip is shearing off with respect to the workpiece, there is going to be a change in the energy here. This is plastic deformation mostly converted into heat, and so there would be heat coming out in both these directions from this primary shear zone. Okay. So, this is because of the nature of the plastic deformation process here, which is really the determinant of the material removal. This is a heat source which contributes to most of the heat release. Okay. So, heat source contributing to most of the heat released, and also referred to as the primary heat zone, obviously because this is the primary reason why the heat is being generated, that the chip is being scraped off from the workpiece. Obviously, a large fraction of this heat goes to the chip, it does also flow into the workpiece, because workpiece is at a lower temperature, and wherever there are two different temperature states, heat flow would take from the higher temperature to the low temperature. There is another reason why heat should occur, and that is because the chip is moving at a certain velocity with respect to this tool face right about here, and so the sliding motion of the chip also generates heat energy, and this energy is primarily generated in the tool face because of the frictional force that the chip would have against which it has to move at a certain chip velocity Vc. So, let us say the chip velocity is Vc, whereas the cutting velocity here in this cutting direction is V. So, there may be a relationship between Vc and V which we need to obtain in order to estimate what is going to be the quantum of temperature increase because of the heat generated by virtue of the rubbing action. Okay. So, there is another heat zone. So, this is typically called the secondary heat zone. So, there is another one which is really this flank, this flank of the tool, and because of the rubbing of this flank with respect to this surface, the finished surface, and we can say that this zone can produce heat due to rubbing of the flank face of the tool with the finished workpiece surface, but obviously if you can have a sharper tool, this rubbing action can be avoided, but in any event this is also known as the tertiary heat zone. which hardly contributes any heat, because if we sharpen the tool a little bit, then this problem of rubbing action of the flank with the finished workpiece would be solved, and there won't be any heat generated because of that. So having said that, now the question is, how can we estimate the different powers which are consumed in the process. So obviously I think I have mentioned many times earlier during the merchant circle diagram analysis of the forces, that the total power consumption of the cutting process during machining is obtained as cutting velocity, or sorry, cutting force times of cutting velocity, or the force velocity product, and I would just assume this to be totally converted into heat. So total rate of heat generation is actually this W, the rate of consumption of the power. We assume that 99% of the power is consumed in you know, the cutting process, because obviously the forces are very large and also the force velocity product is pretty large. So if the rate of heat generation, the primary zone and secondary zone are, let us say, Wp and Ws respectively, this is the rate of heat generation in secondary zone, and this is the rate of heat generation in the primary zone. So then W can be recorded as Wp plus Ws. Obviously there is no other source into which or from which the heat would result. We are assuming the tool to be sharp enough so that the flank wear does not contribute to any rise in heat flow or something. So these are the two sources principally from which this total cutting force is supposed to be consumed. One is the frictional aspect that comes as a temperature rise of the tool face as well as the chip surface, and another is the primary aspect of shear, which rises the temperature of the chip as well as the workpiece surface. Okay. So now let us assume, or let us try to find out what is the chip velocity, and this we find out from the principle of continuity. So obviously the amount of material that is being scraped off is the material which is removed as the chip. So we say the principle of volume continuity enables us to find out what is the volume rate of removal of the material, which is VWT1. I think I had mentioned this earlier. V is the cutting velocity in the direction of the cutting force, W is the sort of width of the cutting zone, and T1 is the uncut chip thickness. So this much amount of volume is being removed, and the same volume is converted as the chip velocity. So if I have considered T2 as the cut chip thickness and W as the width of the cutting zone, so the T2 times W times Vc, where Vc is the chip velocity, would give the same rate of volume as the volume which has been scrubbed off from the workpiece surface. So therefore the Vc, or the chip velocity, in this case can be estimated as T1 by T2 V. Obviously the W components, they all go off because the width is same, whether it is cut or uncut side of the deformed chip or the pre-deformed chip, you know, as a part of the material. So T1 by T2 times of V, this we call as a cutting ratio times of V, and secondary heat generation Ws can be recorded as the frictional force F that the chip faces times of the chip velocity, which is also can be represented as the frictional force that the chip faces with respect to the tool face times of the cutting ratio R times of the cutting velocity. So F R V. So that is the secondary rate of heat generation, which can be plugged in to this equation 2 right about here as Ws value. Let us calculate the Wp. So obviously Wp would be W minus Ws. W already has been recorded as FCV minus F times of Rv. So this becomes equal to Fc minus Fr, where R is the cutting ratio, times of the velocity V. So that is what the primary zone would be enabled to provide as the rate of heat generation. So once we have calculated the Wp and Ws, let us see what is the impact in terms of temperature or the surface temperature. And when a material particle moves across the primary deformation zone, the temperature rise that would be there, theta p, would be given really as the amount of fraction that is lost of the primary heating zone into the workpiece. Okay, so 1 minus that is basically the amount of power, primary power, that escapes into the let us say the chip, okay, divided by the mass rate of flow, which is actually again the density of the material times of the cutting velocity times of T1W, which is the rate of volume removal of the material. So this is the mass rate of removal of the material times of the specific heat capacity. Okay, so Q equal to mCT, as you know. So if the total amount of temperature rise of the chip because of the primary power is theta p, then we can assume that to be a fraction of the power that actually moves into the chip per unit rho v T1 WC, which means it is the mass rate of removal of the material times of the specific heat capacity of the material prior to the deformation. So that is giving you an indication of what is going to be the rise of the temperature because of the primary heat. So here lambda is actually the fraction of primary heat source going into the workpiece rho is the density of the material, C is the specific heat of the material, and T1W is basically the uncut chip area, which is a product of the width of the cutting zone times of the uncut chip thickness. Okay. So there have been reports in the literature which has really determined this lambda from dimensional analysis. So lambda is estimated from dimensional analysis, and I am not really going into the details of these analysis, because from a standpoint of estimating of the temperature we can actually assume this formulation, okay, and work out what is going to be the increase of the cutting temperature in the zone of cutting because of the primary heat component. So lambda can be estimated as 0.15 natural log of 27.5 divided by theta tan phi, where this parameter theta is again a non-dimensional parameter which has been recorded as rho v c T1 by K. C is the specific heat capacity of the material, and K is obviously the thermal conductivity. So you have to sort of create this non-dimensional quantities and try to find out what is the relationship between this fractional of heat release as well as this whole quantity here, and it is found that with respect to experiments as well as the final non-dimensional parameters which are related to each other, it comes out that lambda becomes equal to, it's inversely proportional to the ln of theta, this parameter here, non-dimensional parameter here, and also inversely proportional to tan phi again, which is non-dimensional in nature. So now therefore theta p, that is the rise of temperature from the primary zone or primary contribution, can be estimated. We can similarly do the estimation of the theta s, the secondary zone, and the maximum temperature rise as well as the average temperature rise because of the secondary power. And so in this case what we can do is that the maximum temperature rise theta s, again coming out of literature, has been estimated to be 1.13 root of theta T2 by L Ws, the secondary power, which is actually generated by FRV, as I told you earlier, divided by rho CV WT1. Okay. So obviously this is again the mass rate of flow, okay, times the specific heat capacity, so the m dot c component, and obviously the Ws signifies the rate of heat generation. So the rate of heat generation per unit, the rate of mass flow times the specific heat capacity, gives you an idea of the theta s. So just because, and you can understand that there is if you look at really how the chip is contacting the tool surface, the chip really is having a length of contact, okay, on the tool surface. Let us say this is the tool that is being considered, and this is the workpiece surface, this is the shear zone being created because of which the chipping process is happening, this is the chip process. So the chip really is trying to go out, right. So as it removes, the chip goes out like this, okay, and there is also a finite length which it is contacting on the tool surface. So this length is what this L is, okay, the length of contact of the chip on the rake face, and it basically gives you a an attempt to as a function of this length you can record what is the theta s value. So if the length is lower and lower, and this point is closer to this particular point of engagement of the tool with respect to the workpiece or the work zone, actually the theta s would be higher and higher. That is why this inverse relationship is obtained here. So the this contact length here has again been correlated experimentally. So experimentally people have reported this contact length L varying in relation to T2, which is the uncut chip thickness. Remember this again, T2 here term basically represents the uncut chip, the cut chip thickness, I am sorry, just because this side is the T1. If you may remember from earlier analysis, the cut chip thickness is after the deformation of the chip has happened actually, and here the L by T2 is experimentally found out to be a function of phi, and it basically is represented as 1 plus tan phi minus alpha, okay. So this is also borrowed from an experimental result. So in that event, if I substitute all these values and try to find out the overall form of what theta s would take by substituting the value of phi etc., the theta s maximum, and this is the maximum temperature on the chip or temperature distribution on the chip because of the relatively different lengths of engagements that the chip has with respect to the tool face, we can get this as 1.13 root over, and we put the value of theta here as rho v c T1 by K, thermal conductivity of the material, times of T2, which again can be represented as L divided by 1 plus tan of phi minus alpha. So that is how you represent theta T2 divided by L, because theta T2 by L under the root, that is what it says, and so this get cancelled off, times of Ws, the amount of secondary power, times of rho C V W T1. So this can again be recorded as 1.13 root over 1 divided by rho C V T1 K 1 plus tan of phi minus alpha times of Ws by W, okay, and so that is how you can get the contribution from the secondary zone. Already you have had a contribution of the primary zone by virtue of this value of lambda here as recorded here in this particular statement, 1 minus lambda Wp by rho Vt1 Wc, okay. So an average temperature also can be plotted out as just simply the ratio between the rate of heat generation at the secondary zone per unit the mass rate of removal times specific heat capacity of the material. So this is an average temperature rise, okay. So this is not of much significance, there may be some numerical estimations where this is of some importance, but what is normally important is to correctly estimate what is the overall temperature rise, and the overall temperature rise here in the cutting zone, if I may just look at this particular zone. So there is a heat flow because of the primary heat which is generated, and there is also a heat flow because of the frictional heat which is generated, which is maximum at this particular point. So the maximum temperature here would actually be equal to the ambient temperature theta 0 plus the increase because of the primary heat and the increase because of the secondary heat. So that is how you can calculate the maximum temperature in this particular case. So in the interest of time I am going to close this module, but in the next module I am going to make you teach or make you learn about how you can actually estimate and what are the kind of values or at least order of magnitudes which are involved of temperature rise because of this various thermal models that have been represented in this particular module. So as of now, thank you and goodbye.